Hello students, welcome to today's session. Today we will be discussing the topic Lebesgue measurable functions. So to start with, we will be beginning from the concept of a measurable function followed by some basic results on measurable functions. So first of all, I'm going to define what is a Lebesgue measurable function, or we will simply call it a measurable function. Let E be a measurable subset of R, then an extended real valued function defined on the measurable set E. So I can write this F as from E2, since we are taking it to be extended real valued function. So I'm writing this function. F is defined from E, that is measurable set, to extended real number system. I'm denoting it by R star, where this R star refers to R union with set containing minus infinity and infinity. So you may note that here we will be talking about extended real valued functions, right? So we have considered E to be a measurable subset of R, and then an extended real valued function defined on E is said to be Lebesgue measurable, or you can simply call it measurable, if for each real number alpha, the set, which set? The set X in E, such that Fx is strictly greater than alpha, is measurable. So this is the definition of a measurable function. So what we have to do, we have to consider the function on a measurable set, and the function is going to be extended real valued function. Then our function is going to be Lebesgue measurable if for each real number alpha, this set is measurable. So this is the basic definition of a measurable function. Then moving forward, whenever we will consider some function and we want to make it measurable, then we have four equivalent conditions that can be used to prove that the given function is a measurable function. So these conditions are like this. The first thing is the following. So I will write this as a result. So you may write it as a point to remember. So the following statements are equivalent for an extended real valued function f whose domain E is measurable, so the conditions are like this. Number one, so you have seen that in the definition of a measurable function, we are talking about a set, and this set should be measurable. So similar to this, we are going to write four equivalent conditions for this. So these conditions follow like this. So first part is for each real number alpha, the set x in E such that fx is strictly greater than alpha is measurable. So this is the same set that we have included in the definition also. Now we want to look what are the other three conditions. The second condition is for each real number alpha, the set x in E such that fx strictly less than alpha is measurable. The third condition is for each real number alpha, the set. So I'm just saving time. So the set x in E such that fx is greater than equal to alpha is measurable. And the fourth condition is for each real number alpha, the set x in E such that fx less than equal to alpha is measurable. Now just notice, in the definition of a measurable function, we have used the condition number one to, to prove the function is going to be measurable. So we have defined this condition in the given definition, in the definition of the Lebesgue measurable function. Now, in this result, we have stated that these four conditions, 1, 2, 3, 4, all these are equivalent. So this says that if one want to prove a function is measurable, then the person can use any of these four conditions to prove the function is Lebesgue measurable. So whenever you will go on checking the functions are measurable or not, in then you will be using you will be looking at the sets and you will notice some of these sets will be there. And since the function is going to be measurable, so you can make use of any of the four statements that are given here. So I hope this is clear. So you can take a break of 1 or 2 minutes to understand it. You can pause the video and understand. So later you can start. So I'm moving forward. So now we have seen there are some basic functions. Suppose let me talk about the case of a constant function. Suppose we are given a constant function and now we want to look at this whether a constant function is measurable. So the result is a constant function defined on a defined on a measurable set is measurable. So this is the result. Now we want to verify it, that whether a constant function defined on a measurable set is measurable or not. So you all know what is a constant function. So whatever value to domain you give to the function, it will always return a single value. So that let f be a function defined from E to R star as f of x equal to c for every x in E. Okay, so now we are considering E to be a measurable set. Since the function is defined on a measurable set. So now, now we can fix a real number alpha. So let alpha be any real number. Okay, now we will consider the set. So now consider the set. So for ease, I want to call this set as A, right? So this set is x in E such that fx is strictly greater than alpha. Now you see, the function is given as, so on all the domain points, its value is just c, one constant value. So now we want to see those points of E at which fx is strictly greater than alpha. That means we need to compare c and alpha. So since c and alpha are, if these are two real numbers, then there are three possibilities according to law of trichotomy. It is possible that either C is less than alpha, or C is equal to alpha, or C is greater than alpha. So one of these will definitely happen. So now, what happens if C is greater than alpha? So first I'm picking this case. If C is greater than alpha, then what will happen? So now we know for every point in x, every point x lying in E, the value of function is always going to be C. So if C is greater than alpha, then at each point of E, function is strictly greater than alpha. So I can write the first case that says if C is greater than alpha, in that case, this set is going to be E itself. Because on whole of E, the value of function is going to be C. Now, let us look at the other case. So, can you look at any point in E when the value of C is going to be alpha? So if C is going to be alpha, so if C and alpha are equal, then and f of x is given to be C. So then what will happen? If C and alpha are equal, then f of x will be equal to alpha. But we want condition should be fx should be strictly greater than alpha. This means if C is equal to alpha, so I cannot find any point in this set at which my function is strictly greater than alpha. So it will become equal to alpha. So this is empty set. So on the other hand, if I say my C is less than alpha, if C is less than alpha, so f of x will be less than alpha. So you will notice no point in this that will satisfy this condition that fx is strictly greater than alpha. So again, if I take C to be less than alpha, so we will find no point in E. So that means I can write this set A as, by combining these two last two parts, I can write this set A to be, it is E if C is greater than alpha, and it is empty set if C is less than equal to alpha. So that means now the set that we wanted to verify whether this set is measurable or not, it is depending upon two sets. One is E, other is empty set. And we know that from the hypothesis, it is given that the function f is defined on a measurable set E, which means this set E is measurable. On the other hand, we know that empty set is measurable, right? So since empty set is measurable, This is known to us. And E is also measurable. E is measurable. It is given to us since the function is defined on a measurable set E, right? So therefore, what we got that A is measurable. So A is measurable. Since we have obtained A is measurable, so therefore the function F is measurable. The function F is measurable. So in this way, we have verified a very important function that every constant function is measurable. Next, we will look at some more examples. Let us try to see whether a continuous function is measurable or not, right? So next, we will try to attempt to verify whether a continuous function is measurable, right? So suppose, so we want to verify the constant function is measurable or not. Okay, so let us consider a continuous function, sir. Continuous function. We have already verified the constant function. Now we will be verifying the continuous function. Let f from E to R star be a continuous function. Obviously defined on a measurable set E. Defined on a measurable set E, right? So now let alpha be any real number. Let alpha be any real number. Now let us consider the set that we want to be measurable for this function to be measurable. So consider the set. So again, I call it A, right? So A. So this is X in E such that Fx is strictly greater than alpha. So now if you see, so since my function is defined on from E to R star, so this is extended real valued function. So if I want to write those points of E for which Fx is strictly greater than alpha, that means suppose if this is my R star, so there's a small difference between real numbers and extended real number system. So here we include the points minus infinity and infinity. So this alpha may lie anywhere. Suppose I say my alpha is lying here, right? So what about those points of, so A means those points of E at which Fx is strictly greater than alpha, means Fx is lying on this side, right? So that means I can write this set as inverse image of alpha to infinity. Do you understand it? So I'm taking those points of E at which Fx is strictly greater than alpha. So I can write it in this form that those points, so the inverse image of the points whose image was going to be from open interval alpha to infinity, since here I have considered it to be strict inequality, right? Okay. So what I'm given, we are given that this function f is continuous. So we are given that this function f is continuous. So we want to use this to prove this, to verify whether this function is measurable or not. So let us proceed now. So this set is this open interval this to open from alpha and closed from infinity, right? So I want to write this set in such a way that I can express, I can make use of the continuity of the function. So now if you see, I can write this set from alpha to infinity, the semi-open interval, as complement of the closed interval from minus infinity to alpha. So I'm writing, it can be written as, I can write it as F inverse closed interval minus infinity to alpha and its complement, right? So you can take few seconds to look at it, right? Okay. So if you have understood it, then we will proceed. So now notice the interval minus infinity to alpha is closed. It is closed set. So what about its complement? So its complement minus infinity to alpha complement. We know that the complement of a closed set is open. So it is open, right? So now further, here we are taking inverse image of an open set. So if we are taking inverse image of an open set, we know that inverse image of an open set under a continuous map, under a continuous map is also open, right? Is also open. So this means what? So from here, what we reach, what we arrive at? We arrive at the inverse image of this open set minus infinity to alpha complement is open. Further, we know one more thing that so this means this set is going to be open. So we have reached here. Next, we know that every open set is measurable. Every open set is measurable. So that means since every open set is measurable, this means this set is measurable. So if the set on the right hand side is measurable, so we reach here that A is also measurable. So this means, so from this all discussion, we reach at A is measurable. So this means my function F is measurable. So with this, we have seen that a continuous function is always measurable. So now we can formulate the statement that a continuous function defined on a measurable set is measurable. Okay. Now let us write one more thing. Is the converse true? Now we are becoming more greedy. We want to verify the converse also. So the converse is every measurable function is continuous, right? But we do not know whether it is true or false. We will verify. So now let us look at so we consider a function which is not continuous, right? So consider a function and let us check whether that is going to be measurable or not. Consider a function f defined from closed interval 0 to 2 r defined as f of x is 1 for x belonging to closed interval 0 to 1 and its value is 2 for x belonging to semi-closed interval 1 to 2. So clearly this function is discontinuous at 1. Clearly f is discontinuous at point x equal to 1 in the domain. So we can look at its graph also. So from 0 to 1, the value of the function is 1. So from 0 to 1, its value is 1. And then moving from 1 to 2, so its value is 2. But at point 1, its value is 1. It is given. So I can write. So its value is 2 from open interval 1 to 2. So this is the graph of this function, right? So I'm just marking it so that you understand. The function is discontinued at 1. Its value is defined from this semi-open interval 1 to 2. Now we want to check. Now we have seen that this function is clearly discontinuous at x equal to 1. Now we want to verify if this function is measurable, right? So let alpha be any real number. So now consider the set. Same set A as x in, now in this case my E is 0 to 2, right? So this is my E. My domain is this E. 0 to 2 such that fx is strictly greater than alpha. So now we know my function assumes only two values in this interval 0 to 2. One is 1, other is 2. So that means we need to compare the values of alpha with 1 and 2. So it is possible that so we have to compare the value of alpha with 1 and 2. So what are the possible cases? Now this is very simple case since we have already looked at a constant function. So in case suppose if alpha is equal to 2 or greater than 2. Suppose alpha is greater than equal to. In case suppose alpha is equal to 2. So then we want the function should be strictly greater than alpha. We want to look at the values of x in the domain at which fx is strictly greater than alpha. So we want fx to be strictly greater than 2. But the value of my function is either 1 or 2. So we cannot find any point in the domain at which my function satisfies this condition if I take alpha to be 2 or greater than 2. So that means there are no points. So this set refers to empty set. Next. So if I take alpha to be lying between 1 to 2, if my alpha is less than 2 and it is greater than 1, okay, if alpha sits between 1 to 2, then what will happen? Or we can include inequality also. Now if alpha sits between 1 to 2, then what will happen? Then you can notice that so anything that all points that are lying in this interval, semi-open interval 1 to 2, so these are giving me value of function to be 2. Okay, so in case alpha is 1, in that case you have all points in this interval that satisfy this condition, right? So the value of function in this interval is going to be 2. So that is 2 is clearly greater than 1. In case alpha is strictly greater than 1, so and it is lying between 1 and 2, even then if you get alpha something close to 2, even then that is greater than 2, right? So for this part, I get the interval as semi-open interval 1 to 2. Then the third condition is in case if alpha is less than 1. In case the value of alpha is less than 1, so then because the possibility of the value of function is either 1 or 2. So function either take value 1 or 2. So if alpha is something that is less than 1, then this whole interval satisfies this condition. That means if alpha is less than 1, then the points of this interval that satisfy this condition are full interval 0 to 2. Now, that means for any real number alpha, so my set can take these three forms. If alpha is greater than or equal to 2, it is empty set. If alpha lies between 1 to 2, it is this semi-open interval. And if alpha is less than 1, then this is this closed interval 0 to 2. Now we know that all the sets, we know that empty set, the semi-open interval 1 to 2, and the closed interval 0 to 2, all these are measurable sets. All these are measurable sets. So this gives me A is measurable. So which further means my function f is measurable. So we were looking at the converse of the result, that every continuous function is measurable. And here we have obtained a discontinuous function, which is not continuous at x equal to 1. And however, it is found to be measurable. It means the converse need not to be true, right? So this way, we have gone through the basic definition, the equivalent conditions that can be used to prove a function is measurable. And the final part that we looked at, every constant function is measurable, and a continuous function is measurable, and its converse need not be true. So that's it for today. So in the next lecture, we will be discussing something more about the measurable functions. So in case you have any doubts, you may feel free to write to me on the given email ID. Thank you very much.